So I'm going to talk about work that is not necessarily my work. It's the work of a large team at Microsoft Azure. And I hope you enjoy it. Let's see. Okay. So I'm going to talk at the beginning about why cloud. Try and set the stage. What's going on with cloud and why, and what Azure is about. So we use the term hyperscale. I'll try to give you a feel for what hyperscale means and what enterprise proven and what hybrid means. Let's see, hybrid. So enterprises have already their own data centers, many do, and their own on-premise workloads. And so hybrid means you're okay with that. You want to, if an industry wants to get born in the cloud, you let that happen. If they're already born and living with not yet fully in the cloud, then you need to create a bridge. That's hybrid. So I'll tell you about, there's a lot to that. There's something called Azure Stack, which runs on the premise, but there's a lot of interesting networking stuff that makes it seamless to span the on-premise data center with the cloud data center and move work back and forth. It's not your father's, your mother's, your uncle's, your aunt's Microsoft. It's a new Microsoft. And so we are very open. We're friendly to Linux. We love Linux. We love Chef and Puppet, Ansible, Python, Java. It's all running in the cloud. MongoDB, the popular open source, Docker, and so forth. A lot of the initial workloads in the cloud are what we call dev plus IT. So you want to test in the cloud and then get things right. And for that, you need code sharing and development environments. So Eclipse, GitHub, and Chef and Puppet. Those kind of things have to work, as well as Microsoft's PowerShell and Visual Studio. All of Microsoft's first-party services like Office 365 or Xbox run on top of Azure. And then we also support Salesforce, Box, quite a few other software as a service companies. So, and you can build your own software as a service on the Azure cloud. Boom. Trustworthy. So we have all these certificates that means you can be safe in the cloud. And also what it means is that we respect a lot of data sovereignty. So there are a lot of countries that don't want the data to leave the boundaries of that country. And so we also are certified by that country to keep the data local to the country. And this is causing us to build data centers all over the earth, which I'll show you a picture of soon. I'd like to, we were talking over to you about this, about what does it mean to transform to the cloud? What's going on? And what's really going on is that every business is transforming to the cloud. I mean, really, there's no exception. It's a journey. They're not all in yet. Some, if you think about, a swimming pool, some have put their toe in. Quite a few have plunged in, and all the way, the torso, the head, everything's in. And some are in between, maybe up to the knees. But every business is going to the cloud, and one way to think about it is that what does it give you? It gives you a place to put data, all your data, and your software together, and manage it quickly, flexibly. So this leads to intelligent action. And I can show you slides, but it's nice to tell a story that helps to describe why it applies to every business. And this story I'm stealing from Joseph Saroge, who's our senior corporate vice president for machine learning. And he calls it Connected Cow. So you can find it on YouTube. Just look for Joseph Saroge Connected Cow. But let me tell you about it. Really the point is even farming. I mean, farming is maybe the first business. And even farming needs to get into the cloud. So if I could show my PowerPoint, this would be a video of the cows walking around. But really the question is, why is this cow wearing one of the new Apple Watches? Well, actually, it's a Fujitsu pedometer it's wearing. And why is this cow wearing a Fujitsu pedometer? Well, the Fujitsu guys who run their app in the cloud and sell this service wanted to know how to improve farming. I mean, if you think about farming, you've got fixed resources. You've got land, you've got cows, you've got to feed them, care for them, and that's a fixed. You have your own labor, which is really most of the cost of farming is labor, and you have to produce as much as you can, you know, to be a successful farmer. Milk and meat and more cows. So what happened? This is an interesting story. Let me see if I can push this through. There we go. You know, from high school biology, you learn about this thing called estrus, which is kind of, you know, what we call the animal is in heat. You know, it's in the mood, the magic is right, the music is playing. That's the time to, for this, if you want to make another cow, that's the right moment. And this line here is the line of the amount of steps a cow takes in the course of a normal week, green. And this yellow line is the amount of steps the cow takes just after going into estrus. So you can see there's an anomaly. And so what's happening is on that pedometer, there's a wireless connection to Azure, and then the data is streaming through our pipeline of analytics, and then predicting when is the right time for insemination for this cow. And what does it mean to farming? Just talking to Rayap about this. Farmers already know from centuries, you know, how to figure this out. And they're good, maybe 50-50. But they don't always get the right results. This, with the pedometer method and the machine learning, you can get essentially perfect prediction, and you can produce the cows much more efficiently. So this has, it's a successful application. It's got all the buzzwords. It's got IoT. It's got machine learning. It's got cloud. It's got old business like farming. It's got everything. So I love this example. And it allows the farmers that use this tech to, first of all, produce more cows more efficiently. And secondly, other similar graphs find out if the cow might be sick, and then do something about that by their pattern of walking around. So that's a story that shows, I hope, to you that every business, it needs to be somehow using the cloud or will be disadvantaged. So I was just at, visiting the team in Hyderabad, the Microsoft guys, and there's a team run by Vijay Mantami there that does machine learning. This is an example, if you're a computer science guy, we're constantly deploying in the cloud new versions of the software. And there's millions of hosts in Azure, and there's tens to hundreds of VMs running on each host. And when you try to upgrade the software on one of these VMs or one of these hosts, sometimes it doesn't work. The upgrade fails. And then someone has to come in and diagnose it, like an IT job diagnose it. And this is, the part of the story is, that's not good enough. We want to know why the software upgrade failed and then improve it. So next time we try it, it works, and maybe there'll be a new bug, a new failure mode. We'll learn that too. So we have to pick these anomalies out and then classify them. So this is data science used to infer the rules using some interesting data science that will predict that the upgrade is not going to work out. Then now, instead of having a reactive thing where the engineers are going to try to, as an emergency, patch the software, they're going to look at these kind of reports. They're going to figure out the main reason the upgrade failed and fix it, and create a virtuous cycle. They will fix that. More upgrades will succeed next time and get better and better. So the other thing that it impresses on you is, yeah, if you're building a cloud and you're running services on a cloud, you also use the cloud to do better. You bootstrap yourself. And that's, in software-defined networking, that's a very important thing, that we use the distributed systems, we use the big data, we use the machine learning, all that stuff that comes with the cloud to build the network. How's it working out? Not just farmers, but the Fortune 500 is pouring into the cloud. 80% of the Fortune 500 uses Azure, for example. There's lots of Indian companies that I could have put up here, but I grabbed the slide from our PR team and didn't have them all. But basically, all the major names are up here. The momentum is crazy, and I'll show you some pictures about why. But essentially, there's something like 300 million Azure Active Directory users now on the cloud. 100,000 or so new customers a month. It's okay. So it's an interesting time to be working in this area. You're going to learn something. With this kind of change, you're going to learn a lot, and it's a new form of computing. And again, for Azure, about 1 out of 4 of the apps run on Linux, and 2 out of 3 apps are third-party apps, not necessarily Microsoft apps, but third-party apps that are running in the cloud. So I'm going to tell you a little bit about what's under the hood now. How do we build this network for the cloud? And I'll tell you what hyperscale means, this word hyperscale. I'll show you a picture. And software-defined networking, and then some interesting new things in the future. And I could tell you more also if you're interested in any part of this, demonstrate some of it. So this is what a computer looks like nowadays. This used to be what a computer looked like. But this is a truck here, right here. That's a truck. And this is a data center. So the scale is amazing. One of my colleagues, Dave Maltz, is really wrapped up in building these things. And they're getting bigger. So we built about 6 or 7 on this campus. This is a new one going in. You can see that other one in the distance. So, when you can have up to 500,000 servers in one of these data centers, and 10 to 100 times more containers. The containers could be VMs or could be Docker containers, other kind of containers. That's what our computer looks like. So there's various ways to improve. One way is power efficiency. So we keep using, to get the same amount of computation done, we use less and less power over time. This metric called PUE is cannot get below 1, so we're getting closer and closer to 1 in terms of power usage efficiency. And things are more software defined. What does it mean to be software defined? So if you're building this many servers and networks and power and everything, then there's no way that it can be kind of done by hand. It has to all be controlled through software. The building, the running, the whole life cycle through software. And I use the term, I don't know if you guys play with Legos. I played with Legos when I was a kid. Those are Legos. It means you have to find standard parts, common building blocks, and build the entire cloud out of those common building blocks. And the other thing is, another way to think about this is t-shirt sizes, like small, medium, large. You don't do bespoke t-shirts. You build only these 3 kind of t-shirts, and then you decide which of the, for which scenario to apply which t-shirt. It's through this kind of massive regularization, standardization, that you can actually control the whole thing through software. And that's the big change for all IT. If you ask the IT guys that work here and so forth, they'll have a closet that's built one way and another closet that way and wires this way and that way, and that's just not going to work. You can't do it that way, and this is more like going back to the farming thing. This is like industrial farming instead of a gardening. You have to engineer everything. PDF is not going to work that well. Anyway, so this is some kind of artist's map of Azure data centers. We have we have 3 now new ones in India, in Chennai, Pune, and where's the third one? Mumbai. Yeah, sorry. Maybe one day we'll get to Delhi, and we have 20 going up to about 50 or so data centers across the world. Now these data centers are like campuses, like I showed you, that have multiple buildings in them. And Azure just opened up in the UK and in Germany data centers. I'm interested to see how this one turns out. Okay. So we also have content distribution network locations, hundreds of them, and hundreds of smaller remote data centers, small data centers for accelerating content. So we actually have one of these small data centers in Delhi. So if you're close to Delhi and you go to Bing.com, you'll hit that small data center, and it will accelerate. It'll make Bing feel faster, but it doesn't do the full Bing search and all that stuff. That's in one of these mega data centers. We have quite a few of those, and then we meet at the internet exchange points. There's something called that I'd like to tell you about called ExpressRoute. So if you're an enterprise, you may already have a deal. Like in India, you may already have a deal with Airtel or Bharti or Tata. And like this university might already be on one of those carriers. And then if you want to attach Azure, just like click the mouse, attach Azure to your network, then we have a deal called ExpressRoute where you can attach. We already have done the relationship with the ISP like a Tata. So now you can attach Azure to your private network. So if I'm here at IIIT Hyderabad and you're on Tata, then you don't have to change any wires, and suddenly you're in Azure, and you can start provisioning service in Azure. If you're a major enterprise like like Tata itself, for example, then you can run fiber straight to internet exchange points where we will meet you. This means you can reach Azure without going over the internet, and at high speed with quality and so forth. And this turns out to be incredibly popular. for enterprises. They don't want to traverse the internet to get to their private data. And it's not going to show, I think. Let's see. It doesn't show, but I had a picture of all the different partners that we have. BT, Deutsche Telekom, AT&T, Orange, Tata, and so forth. Okay, let me tell you about software-defined networking, SDN, what it's all about. It's interesting that it's built on some principles that came from virtualization and compute and storage, and it's just reapplying these and to networking. And these are the most important things to remember about building a cloud service. Scale out. So scale up is like the mainframe idea. You have a nice box that can do everything, and it's kind of reliable. And scale out is have lots and lots and lots of boxes that can do small things well. They're individually not as expensive and not as reliable, but together you can get crazy reliability and crazy low cost. So it's scale out means single components replicated, like little Lego blocks, or like RAID in data centers. In databases. With lots of devices and small things, they're going to break. It's okay for if you have lots to have 10% broken. You have 90% working. So instead of sort of trying to make each one perfect, I don't know if it's the right word, you embrace failure. You're okay with failure. And you just make sure the failure is isolated and doesn't ripple across the plant and has small impact. So failure is fine. And then use the cloud to build the cloud. So if you have a monitoring problem and you want big data and analytics and machine learning, then, well, you have that in the cloud. So you use that. And if you need a distributed system, you have that in the cloud. So, and that's what the example I showed you from Microsoft Hyderabad for failure to upgrade. And I'll show you more about that. Then the control plane. So centralize it and always have this notion of a target state. Or we call it a goal state, G-O-A-L state, target state. And what it means is that every device has a role, and given its role, you want to make, and get it into a certain target state and let it function and behave in that target state. If it drifts away from the target state, return it to the target state. So you'll have a state transition diagram that always tries to push to the target state. Whatever the state it's in, it'll say, wrong behavior, move this way, this way, this way, and get to the target state. And that's, for networking, that's different. In networking, traditionally, you sort of plug stuff in, it discovers, oh, here I am, who else is nearby, and let me connect to them, and then do my best to create global connectivity. In the cloud world, you don't do that. Nothing just gets plugged in. Everything is engineered, and given a target state, you relentlessly drive toward the target state. So the way it works is you have resource managers that service requests, and they have in mind system-wide objectives, not just their own little. The resource managers have the big picture of the entire data center or the entire region, depending on their scope. And they're making optimizations and allocations that have in mind the global objective to get the work done and also be efficient. Then the resource managers have also the persistent data. The resource managers talk to controllers, and the controllers are stateless, but they have their sort of goals given to them by the resource managers, and then they orchestrate the driving of the state transition diagrams to the target state. The controllers talk to agents that are down there at the bottom, on the servers or other fundamental elements, and they listen to the controllers and just do what the controllers tell them to do and never give up. And these principles are in everything we do. So if there's one thing to remember about cloud, these are, I believe, it's in here. So let me tell you what physical networks look like nowadays. Imagine, that picture I showed you with all those buildings, and in them there are these racks of servers, and the servers are here and in light blue, and then there's switches. I should have had pictures of them, but they're simple. We call them pizza boxes. They're amazing ASICs inside with like 7 billion transistors per ASIC. But the ASIC is, think about $1,000. Not that big a deal. It's just that they're stamped out like crazy, and they're running in each of these switches. And then these switches down here, we call them tier zeros, talk to the next layer up. Sometimes we use the term spine at tier 1, and they're fully meshed above from this cluster up to a tier 1. So you can see there are lots of paths to get from here to here. I could go this way, I could go this way, I could go that way. Lots of ways to go. And then these guys are then create a larger scope. They can get to the next tier, spine, tier 2, and then a third tier, tier 3. So you can go from rack, think about 100 servers, to a row, think about 1,000 servers, to data center, could be 100,000 servers, to region could be 500,000 servers, something like that. And there's one network. This is a lot of fiber. So I think in the pictures I said 1.4 million miles of fiber. I guess you can loop that around the moon a few times. And there are lots, you can see there's lots of paths. So getting to my principle that if something fails, it's okay. I've got lots of other things that are still working. This is a high-speed NIC. This actually is a 3D printout of a 40 gig NIC, 40 gigabits per second. The new NICs that we're deploying are 25 gigabits per second or 50 gigabits per second. So these servers down here can pump data fast. This is a rendition of the old school networks that we used to build. We call them snowflakes. A snowflake is a unique, beautiful, but fragile object that's carefully, each one different. And like here are two perfectly fine snowflakes. So that goes against, there's no replication, there's no Lego thing, there's no sort of replicated small components. Things were sort of done in pairs, like twins. If one of them failed, I had its twin that would take all the load. That meant that thing had to be 50% loaded because it had to take all the load of the other one. If they both fail, you're out of luck. They kind of try to impersonate each other. So if this one fails, the other one say, oh, I'm him. And it was kind of tricky to make it work. And because it was tricky, you had single vendor solutions. Like Cisco could make an all Cisco one work. Juniper could make an all Juniper one work, and God help you if you tried to mix. Whereas this is simple, standard, commodity, mixing is fine, and things work. But there are some challenges, which I want to tell you about. So there's lots of stuff. There's lots of these switches replicated. There's lots of fibers. And again, they can break. And we're talking about, it'd be great to show you, it's a needle in a haystack. Which one is broken? Problem. And then they can not completely break, which is the worst part. They can, a switch should not drop packets if there's no congestion. But if there's some kind of defect, it might drop 1 in a million packets. If you drop 1 in a million packets, then some big data workloads like Hadoop will see it and start reacting to it and duplicating the work to cope with the failures, and you could get a cascade that's not good. So we call that a gray failure. It's not, white, it's not black, it's in the middle. So how do you solve this? Well, first of all, we model everything. So if you think about the networking problem, it's a high level. It's like a graph problem, where you have this switch that needs to go to that switch. It's got a link in between it. It's like a graph. It's a very, I would love to show it to you, but it's a complex graph. It's a graph that's more complex probably than any graph you've seen. It's not like if you're going to school, you pick up, we're using A.O. Hopgraph enrollment or some textbook now. You read about connected components and this and that. It's more complex than that, but fundamentally, it's a graph. And so what it means as an engineer is you've modeled everything in this graph, and now that graph is your truth. Okay, what's down there in the data center is not your truth. It's trying to be your truth, and if there's a deviation between your truth in this graph and what's in the data center, you got to go fix that. And by you, I mean the software. So you have this graph and software to track the graph. Actually, it's interesting if you do graph theory kind of things. Now, all your graph theory ideas, K shortest paths, and whatever you come up with can be implemented with this framework. And then you can do some interesting monitoring to find and stop gray failures. What do you get from this? The cost to build one of these mega data centers with these principles, and in dollars, and then the cost to operate it is roughly 100 times better than the conventional Snowflake data center. So we use abstraction. So here is the messy reality. You've got the red line, and above you've got this graph manipulation system. And you can monitor what's down here, and you can update what's down here. So reality, graph. And here's those, remember I told you about there's the target state. There's also the real state that you observe, and you have applications that propose a transition, from the observed state toward the target state. And it's happening every millisecond across these huge data centers. If there's a conflict between the proposed states, then you'll sort that out. You have to have distributed systems to deal with those conflicts. And everything up top is centralized with the resource manager, controller, and agent methodology. Here's an example. My daughter does physics, and she told me that is what an alpha particle looks like. I don't know. It's got 2 protons or something like that, 2 neutrons. I don't know. So the solder joints in silicon spontaneously emit these alpha particles. I don't know why they do, and they go into the silicon and cause transient errors. Okay, which if you're building a network, that can mean that little chip that's supposed to be routing a packet from this point to that point now has a bad state, and you may not have any counter telling you it's in a bad state. The alpha particles hit it in the wrong way, and it's in a bad state. That's a problem. It causes parity errors. You also have dirt on the fiber. There's lots of fiber, and in the process of installing the fiber, there can be vibration and so forth, creating dirt. This is the enemy of the network I showed you. So we run software all the time that's looking for these conditions. Do I have the condition of the one with that parity error or dirty fiber? And then it says, okay, seems like this component's sick. I will turn it off. The routing algorithms will find another way, and you won't drop the packets. This one we call traffic engineering. if you, if normally, traffic has a diurnal pattern. Every day the traffic, goes up and down and so forth. And some things are urgent, and some things can wait and be delayed and done when, let's say, let's say at the middle of this valley, when there's nothing else going on, you can do more workload there. So we have other software that understand the traffic patterns and then provide a way to prioritize traffic and to schedule traffic. So I can say, okay, well, this is important to me. This should go in a day, but I don't care whether it's at this moment or 24 hours from now. It just has to get complete in the day. And we have a bandwidth broker that will find when to transmit so that I can fill up these valleys with traffic and get more utilization out of my network. So I want to tell you a little bit about the monitoring, and I like this example because it illustrates this principle of using the cloud to build the cloud. We have an application called Pingmesh, and in every server in this data, it's an n-squared thing. For every server going to every other server, we ping. Okay, and so that's a lot of pings. It's 200 billion probes per day in one of these data centers, and it generates a lot of data, but that's okay. We have lots of disk in the data center. So we just do this brute force stuff. We ping everybody, and if there's an issue, it'll show up as a red dot, and they'll be transients. So there could be a little glitch, and you get a few red dots. But then if there's a persistent issue, it'll show up like the flag of some country. This is probably what some country's flag looks like. And it means that there is a pod set. A pod is one of these small scale units, like a cluster. Or there could be a spine that goes down. And this is a visual way to look at it, but you have machine learning and automatic alerting saying, this kind of data is coming from the Pingmesh. I know it's broken. I'll go take automated action. So that's how we manage the gray failures, these kind of techniques. If you're interested in any of this stuff, we work really closely with MSR, and this is in a paper, and almost everything I've talked about is in papers. Here's another one called Everflow. The idea of Everflow is that it's something like the forever thing, or all the ways. So a flow is a sequence of packets transmitted that match some predicate. There's something about them that's in common, and they're close by in time. Say, all the flows to Google over some time, or this and that, whatever the predicate you want. So there are lots of flows and lots of ways to define flows. And so why not have a super flexible system on every switch that can capture every flow you're interested in? That's Everflow. And so we built this. And so if there's any issue, we can say, let me capture all the packets that match that predicate that are part of a flow. And I can catch it on this switch, on this switch, on this switch, on this switch, on this switch. I can see now I put a lens just for that predicate on the network. And that can then flow into the distributed storage and the machine learning and so forth. What else can you do? I'll tell you a little bit about how we use simulators. If we have this graph and we know something about the traffic, we should be able to simulate failures, right? And simulate changes and then do something about them. So the topology is the graph, the demand is the traffic, we have the policies, we have a simulated service, and we have applications on the right-hand side. Now, what good is it? There's a little bit of math. I thought since I'm here in academia, I'd show you that we do a little bit of math too. So you can calculate the traffic matrices very, very accurately. And that's what this math is doing, the demand matrices. It's taking all the data you've got, maybe there's some wrong data, maybe some missing data, and finding the most likely traffic matrix, where the traffic is coming from, where it's going to, that explains the data. It's a little bit sometimes like this. You know, say you're getting into a subway system and you go through the turnstiles, and all you might have is the turnstile, like how many people pass through this turnstile, how many people pass through that turnstile, and now you have this inverse problem. Well, where were they going? Where, you know, what is the coming from and going to? That kind of inference problem we can solve. We have other data too that makes it possible. And then there's this is a networking thing that influences how the traffic flows, called a label switch path. And then there are constraints like I can't send any more traffic on a link than the link capacity. Or then I have sort of humble goals that I won't be able to necessarily know the exact traffic, but I'll get a lower bound or an upper bound. And hopefully they'll be close. So what you can get from that is a build plan. What am I going to build tomorrow? There's lots of places I can add new capacity. I can simulate all the failures I can have, and I want to be surviving each of those failures. What that means is, after the component fails, I want to have plenty of spare capacity to still keep going. And maybe there's a place, I don't know, from Helsinki or someplace like that, where there's not enough capacity after a failure. Then I will find out by failing it in the simulator, pushing the traffic simulated through, and then figuring out what to build. And so I'll build a plan that will then go order fiber or whatever needed to augment the capacity. You can do this 1 day from now, 1 week from now. You can start forecasting the future. Of course, as you go out years from now, then there'll be uncertainty what the traffic will look like. But you can do lower bounds and upper bounds there too, and pick where you want to live. So that's how the simulator is used. It's, you know, it's interesting to me. So math and you know, tools, mathematical thinking gives you a lot of tools for building systems. You know, it helps you to understand systems. But it's really interesting when math can actually tell you, order this part and put it here. And it's quite thrilling. Yeah. This, the WAN is the wide area network, and so all the wide area network devices are also modeled in the graph. And we have a project called SWAN, for SDN for the wide area network, where we use this resource manager, controller, agent framework to actually pick the paths in the graph. If you think about networking it as an abstract problem, you've got a graph, you've got to put paths in the graph, you've got to push the packets along the paths. That's the problem. Things are going up and down, the graphs can be kind of volatile, you have to track that, but that's the basic problem. And that's what the SWAN network solves. Virtual networks. So, you know, in my own career, I actually switched to work on the cloud because I wanted to work on virtual networks. Virtual networks, I think, are probably the most important thing. If you hear the word SDN, you should think of virtual networks. Really what it means is you don't have to touch anything and you can create a network. Whatever kind of network you want to create, you can, in a millisecond, create that network. And there's no moving parts. There's no logging in and doing some voodoo magic on some strange device. You can go in and do some regular thing on an API and create a virtual network. So forgive me, some of this terminology is Azure specific, but it helps It should help describe things. So we have something called ARM, which is Azure Resource Manager, and it deals with resource groups, that red ring. So a resource group might be, hey, I want a Redis cache, and I want 50 VMs that are going to be doing my data streaming, and then I want another 20 VMs that are going to do my load balancing, and I want some other VMs that are going to do the aggregation of the data. And you have a whole bunch of resources, and you describe all those resources as a resource group, okay? And you don't even have to specify ahead of time how many instances, the 50 and the 10 and the 4, whatever it is. You can let that be free, okay? You can that instance count you can bind later, and that's called a scale set. So I can define how many replicas I want at some other time. Now, I think the blue ring is a virtual network. So if you're a network guy, you're saying, I have these things called subnets, and put the resources in these subnets and these other resources in these other subnets. And you can specify how many subnets you want and what security policies you want. And then you can build up your VMs. It's called the VM scale set. And for each VM, there's a template. So it has so much memory, it has so much disk, it has so much CPU power, and it has so much networking power. The NIC is a network interface card. So much storage and so forth. So, and each of these things can be templated and described independently. So you can template your network piece, template your storage piece, template your compute piece, and then deploy the whole thing as a fleet. It's a nice way to think about things. It makes it easy to manage your service in the cloud. And you can do this by software. You don't have to go through a portal and do this. You can write software to do this. So as a, maybe I'll use, this is great, I can use the Blackboard. If I think about, for networking, there's sort of a portal where you come in as a user. And then you can go down into this thing called the NRP. And at the end of this game, you're going to have your resource group provisioned. So this, the NRP is the part that I'll tell you about next. So it has APIs to manage the networking resources. It's independent of computing and storage. And because it's one of these resource managers, it gives you agility. If you want to do a new resource group every millisecond, you can. If you're a networking guy or a storage guy or a compute guy, you can innovate independently. Networking guys can do new networking features without coupling to the compute guys doing their compute features. And the other thing that's interesting is you can build analytics on top. So you can see how many different types of objects are being used and why. Yes, I can't do the demo for you. Let's see if I have some pictures. Yes. So if you go to this web page, if you just search for Azure Quick Start templates, you'll find it. And then you can pick one of these templates, or you can create your own template for scalable VM scale set. This, even in the front of the room, you won't be able to read this. But what it'll ultimately generate is a form of XML that says, this is what I want. I want a certain kind of network interface. I want a certain number of load balanced endpoints. I want certain kinds of access control, other kind of networking policy. And there'll be a network section that has a profile that'll then guide the deployment of everything in the network. So the way this works is this NRP will talk to, this is a resource manager. It will talk to controller where they'll talk to agent, lots of agents. Actually, these are, there are multiple of these that will then, the agents will then create your resources in the cloud, and you'll be in business. This is just an example. If you're a networking person, imagine a typical IT task. You want to set something up, and you have you'd like to give multiple IP addresses for different purposes to the same VM. Let's say some IP addresses are for coming in from the internet, some IP addresses are local, some IP addresses have certain access control on them, and so forth. And you'd like to support soft attach. You'd like to softly attach, by soft I mean change it. I can dynamically attach an IP address here, and then say, actually, no, I'd rather have it over here on this other VM. I can move it. And then you can support lots of different IP addresses. What can you do with this? You can do lots of websites on a single VM. You can do virtual appliances. So again, if you're a networking person, there are load balancers and firewalls and things like that that typically are a piece of hardware that you would get and deploy and wire up in the cloud. Sorry, not in a conventional network. Those things are now virtualized. And so you can automate the entire process of wiring up these virtual firewalls, virtual intrusion detection systems, virtual load balancers in the cloud through this mechanism. And it extends to containers. There are Windows containers or Linux containers, things like Docker, and it's resilient. So you can do soft failover to a service to back up VMs when a primary fails. I won't be able to do the demo for you, but the demo just shows that I can have one VM that has multiple IP addresses. I can move the IP addresses around, and the service keeps going. I can support multiple websites in the same VM. So how do we do this? This is another sort of thing to try to remember about what happened. What's going on in networking? What's What's this big deal with SDN? If I think about 5 years ago, if you wanted to buy a firewall or I'm doing 5U. It's like 5U. It's a certain amount of room in a rack would be dedicated to a physical networking device that I'd have to buy and deploy. And that would contain everything I need to manage and control and forward data on it. And this is like I want to call the mainframe's counterpart in networking. And then what SDN said is, okay, forget about that one device that does it all. Like one, and pretty much the entire networking industry was all about that. And this is why the networking industry is being completely disrupted, and all the traditional companies are trying to react. I will take this piece out altogether. That'll be a resource manager, just distributed systems. Same with the controller. That'll be a distributed system. It's not in the device at all. And by the way, all I need from the physical network is forward the packets, be reliable, and nothing fancy. Again, Legos, simple. All the complicated policy stuff like firewall rules, intrusion detection, denial of service, attack detection will run on the servers in the host. Okay, so this is if you're a Cisco guy or a Barracuda guy or one of these. This is very fundamental. Your piece of hardware has now been chopped into 3 separate services. None of them require the physical piece of hardware that you were selling some years ago. Now, you can virtualize that thing if you're a Cisco guy or a Barracuda guy and deploy that in the cloud, and it'll run down here in the host. So the function doesn't go away, it just moved. This is a picture of a virtual network. And there's a green company and a red company, and they have secure ways and high-speed ways to move these are VMs, these blue things, move their VMs into the cloud. Pretty much every enterprise understands VMs, already is in VMs, and they know what to do from these across these secure tunnels. And then the VMs will be sitting together on the same server, in the same host, securely. It's okay for, I don't know, British Petroleum and Exxon to be sitting on the same host with their VMs there. They're protected from one another. Coke and Pepsi, whatever you want to use, sitting in the same host, they're secure. And they're secure through the hypervisor. The hypervisor keeps them distinct. And you know, the networking stuff is that in this building, I'm sure every private network numbers their IP addresses out of this, what's called RFC 1918 space. It starts with a 10. So this one starts with a 10, the green one, the red one with the 10. And so they should overlap, and there's a threat that, you know, Coke will send a packet to Pepsi, which is not what you intend. But because they have the same names, right, the same IP addresses. But it's okay because the hypervisor keeps them distinct. Some of the problems we have to solve, there's another buzzword called network function virtualization, NFV, where you create software load balancers, application gateways, VPNs, the ExpressRoute thing I told you about, layer 7 load balancers, all virtually in the host. And they have to be created on demand when a customer wants them. Here's a few modalities of that. You're in a customer data center. You want to traverse the public internet. And so we will create a virtual VPN device over here, and you'll have a physical VPN device, say a Palo Alto device or a Cisco device or a Juniper device. You'll be running here, and they'll create a secure tunnel and you know, an efficient, resilient one between your data center and Azure. There's the ExpressRoute where you go to a partner location. There's a company called Equinix, interesting company, where it's a fiber hotel where everybody brings their fiber and they meet each other there. So if you've already brought your fiber to an Equinix site, oh, we're here there too, Microsoft's there too, and we'll pick you up there, and there's software to automate all that. Or again, if you have all these customer sites and you've outsourced your wide area network to a Tata or an AT&T or someone, we're there too, and you can attach to Azure. All of that's done through software, none of the physical devices and wiring needed. I think I'll skip this. Let's see. So what does it mean for technology? And this is interesting. Inside a single host, you could have 100 VMs. So you would think, oh, well, they talk to each other, right? So I need a network there, and it has to be a pretty capable network. And then there's the other host, and they have to talk to each other. So you need a lot of networking in the host itself. And so you wind up creating what we call a VM switch. The one from Microsoft is called VFP. There's a popular open source one called OVS. And this VM switch can do routing and firewalls and all kinds of networking functions. And I'm going to tell you a little bit how it works. First, it can do all the SDN stuff. It can do address virtualization. That's the, you know, I showed you the tin space was for the green and the red. It can deal with that. It can do software load balancing. What is load balancing? I have this virtual IP address. Let's say I try to resolve Bing.com, and I come up with a single virtual IP address. Well, underneath it, there'll be lots and lots of dedicated or direct IP addresses that are hidden from you behind that virtual IP address. And that's the load balancing problem, is to pick one that's kind of not too loaded and send your traffic there. I can do all the security stuff. And it's done through a certain kind of table processing. And if you follow the OpenFlow world, you'll see it's very close to OpenFlow. It can run at high speed. It also runs on Windows Server 2016 coming this summer and in Azure. So what happens is, again, from the network resource provider, you get descriptions of what the customer wants in terms of virtual networks and the different resource groups. They flow through the controller, and then the controller is going to program the agent or talk to the agent. I didn't show an agent here, but there's an agent here. It's really the VFP agent. And we call it the network manager agent. It will then program these tables. And these tables are interestingly agnostic to traditional networking. They're saying, I'm looking for this pattern. And if I see this pattern in the header of the packet, I'm going to do these actions. And these are called match action tables. Okay, so if you look at the OpenFlow world, it's all about match action tables and stringing together match action tables. It didn't really take off in the physical devices, but it's big time taken off in the host in network virtualization. So then the packets flow through there. Really, the hosts are great, but we want to save the CPU on the host for running VMs and running machine learning and all that great stuff. So we don't want to spend it all on networking. So there's a table offload function that goes to a special device called the Smart NIC, which does this, does the work that I showed you with that. I see this pattern, I take this action. And it can do more things. It can do encryption, it can do low latency transfer, it can do quality of service. So we're building one of these. We've already deployed huge numbers of these. This thing in the middle, so this is interesting. So the old way of designing network interface cards is you talk to a vendor, let's say Mellanox or Broadcom or Intel, and you say, here's what I want. And you give them your request, and so does everybody else. And Microsoft's buying a lot of this stuff, so it's persuasive, but not that persuasive. You're not going to get everything you want. And you're going to get it 3 years from now. Because when you build an ASIC, it takes time to get all the testing done. If you make a mistake, it's catastrophic if you have to do a respin of an ASIC. You're going to get less than what you want. It's going to take longer than you want to do things ASIC style. FPGA is reconfigurable computing. So you can reconfigure what the hardware does when it's necessary to, once a week or when the time is right to do the reconfiguration, because you're going to light up a new feature. You can do reconfiguration on here. And this is the NIC, this smaller thing. We'll still do the heavy lifting of pushing packets and the MAC stuff, the access control, but the NIC is going to do all the value add, the FPGA, the value add stuff. This is just a high speed port. And so Microsoft builds this board, and we program that NIC. If you follow the FPGA world, there's something called Catapult out there. Bing published a lot of stuff that they're doing on it. So you can think about, Bing is, say, on this area here, and the networking is on this area here. The great thing about FPGAs is that you have a lot of parallelism, and you can do sort of directed acyclic graph type flows very efficiently. This is a challenge for us, because now we're coming to terms with hardware that's like software. We can develop and change it like software. We can reflash this thing, If you think about having an Android phone, boom, it's an iPhone. Boom, it's an Android phone. You can reflash it, give it new personalities whenever you want to, whenever it's necessary to. Here's another interesting thing, the Azure Cloud Switch. This is called the Switch Abstraction Interface. Those amazing ASICs are built by different vendors, and you don't want to have to change all your software, the ASIC in the switch, not down the NIC, if you pick a new ASIC on the switch. So the Switch Abstraction Interface gives you a software abstraction layer, and that's open source. There's something called OCP, which is for Open Compute Platform, where you can pick that up. This little picture of an interop demo we showed with, I think, Cavium and Intel maybe, and Broadcom and others, Mellanox, all running on the Switch Abstraction Interface. The interesting thing here is that the same principles I talked about, the target state, the observed state, all that stuff, it's happening inside the switch. Remember the T0, T1, T2, T3? Inside there, you're running a little copy of that same kind of idea. It's got a target that's persisted, and you're moving the observed state to the target state. And the sync agents that are programming the actual ASIC down below. So that's working. That's Azure firmware running on the hardware. So that's also coming. So I think that pounding is telling me I better wrap up the talk. Here are the takeaways. The first part, that everything is moving to the cloud. Every business is moving to the cloud. These clouds are big and growing fast. The biggest pressure on the engineering teams is the sheer pressure of building tons of clusters, tons of everything to keep up with the pace of growth. And how do we do that? Well, remember we Legoize. Everything's like a Lego. Everything's T-shirt. Everything's software control. Nothing is just plugged in. Everything has a role, a mission, and you have a controller that drives it always to that target. And those scale out and not scale up. Every time, we get to design something, that's the way we do it. We use those principles. Networking's own pillar. So in earlier days, networking is kind of entangled with computing. So and storage. So it was hard to tear apart and innovate in networking without breaking dependencies with computing. So through this network resource provider, I can change the template for networking, and suddenly I have a new NIC and a different network behavior, and the compute is stable. And then to build this massive scale thing at low cost and high reliability, you have to innovate across everything. I just told you about a few of the things, but Microsoft does a lot of work at every level. So, I showed you fiber, across the ocean. We do that. We we optimize the optical network, and we do the smart NICs. We do some hardware and firmware, although now it's getting to be a blurry line between software and hardware, and higher level applications like intrusion detection and DOS and virtual appliances. So it's really lucky to be working in the cloud, because you have all these degrees of freedom. You can change whatever needs to be changed. You have, in Twilight Zone, he says, you control the horizontal and the vertical. You control the horizontal and the vertical. If you want to get something done by changing the host, you can change the host. If you want to get it done by changing the switch in the middle, you can do that. So it's a time of interesting churn in ideas, and it's fun to be in working in the cloud. That would be my career advice to everybody: work in the cloud. whether it's Azure or someplace else. It's pretty great. Okay, take questions. Yeah. Oh, okay. Sure. Yeah, so security is always in our minds, and one thing that we do is that's super important is being able to patch quickly. So if a security flaw comes out, sometimes you'll see these advisories. We don't want that advisory to hit the news until our millions of VMs and so forth are patched. So we have to have fantastic deployment systems so that if there is a vulnerability, we patch it. Then in terms of the controller, or the hypervisor, that has to be from the beginning secure. If you could subvert the hypervisor, then you could steal service, you could do all kinds of stuff, bad stuff. So the hypervisor, by the way, if you run Windows 10, you can just, if you want better security, you should enable your hypervisor because it's got better security than, even if you're just running one job at a time, it's got better security. So everything is under a hypervisor, or in the case where we're running native, something very close to the same functionality as the hypervisor. Then channels between the controller and the host are all cryptographically secured. And if anything goes wrong, we are constantly running penetration tests. We have red teams that try to break it. We get these certifications because those red teams were unsuccessful. So it's a constant challenge. And if God forbid if there's ever a break, we contain it. We detect and contain it. So I'm not saying we have had breaks, but you have to imagine the worst. And if there's ever, you have to think in terms of the worst case and be ready to contain any kind of break. But the main thing is this is designed in a way that security guys like it better than conventional networks or conventional devices, because they have this control, they have this global view. It's a more engineered, regular place to implant good security controls than conventional computing. So I mean, anything that lives on a server was put there intentionally, and so it's a clean place to live. Yeah.
Again, the security perspective.
Yeah.
How do you implement Chinese voice security?
Oh, okay. Okay.
It's all shared resources we are talking about.
Right. Yeah. So they're really fundamentally the answer is through the hypervisor. So if you run multiple VMs on the same hypervisor, and you have the right controls, they can't see each other. You can't shake one and feel it over here. There's no way to read data across one to another. So the operating system provides a layer of security that's quite tight. Now, I mean, everything is networked, right? I mean, if you think you can get physical security by putting it on different servers, that's not going to get you there, right? So physical separation nowadays, I mean, when I started working, it was a challenge to get the bit from here to here. Now it's a challenge to not get the bit from here to here. So physical stuff won't get you there. You have to have the right virtual controls anyway, and the right encryption and those kind of things. And that's what we do. Yeah.
One more? Yeah, okay. So the resource manager is controller.
Yeah.
The resource manager is the controller, the software defined network. So what is the operating system on the software running?
Oh, okay. The base operating system is Windows, and Hyper-V is the hypervisor. when you say for the controller, we use heavily a microservices fabric called Service Fabric, which is available on the net. You can download it and play with it yourself. So if you think about, a failure mode would be to build a monolithic controller that did all that stuff, did the software load balancing, the policies, the IP address, and the software. So instead we build, little microservices. All I know is, let's say, what a VIP is, and how to assign the virtual IP address. And then another one deals with MAC address assignment and so forth. And they use the Service Fabric system of distributed collections and key value stores and all that stuff to communicate to one another. They elect, if there's, let's say you build a distributed system with primaries and secondaries and so forth, and the primary dies, it'll reinstall the primary someplace else and rehydrate all the data and sync up all the others to it. If a secondary dies, it will also reinstall a new secondary. If I want more secondaries, I can create more secondaries. If I want to partition, like some of the primaries in this part of the data center and some in there and some in there, so that I can update things. So I can make sure that when I update a host, the secondary is on a different host. So it'll just get elected. Service Fabric will allow me to partition so that the update domains will be taken care of. So this allows us to build and extend our controllers without breaking the fundamental parts of them. So we love that kind of microservice framework for that. Okay.
Team, I'm sorry we're running out of time. I know there's many people with questions. I myself have several questions, but I think we're going to have to take them offline,
Okay.
if you will.
Yeah.
Okay. With that, I want to thank Dr. Greenberg for being here and taking his time.
Okay.